So I'll introduce the session and then introduce both the speakers, and then Thomas will go first and then Hussein after that. So we have two really good talks in the next 1 hour. So they're talking about the tropical ocean hydroclimate and temperature from coral archives. They'll be talking about the paired coral oxygen isotope and strontium-calcium proxies from corals as a way to reconstruct climate on seasonal till decadal timescales and going back all the way to the LIG. And they'll provide an overview of the Pages Coral Hydro 2K project. Right, so very quick introductions. So Thomas Felis is a senior scientist at Marum at the University of Bremen in Germany. He has worked extensively on reefs from across the world, and it's what we were just talking about. They're all picture postcard places. The Mediterranean, Polynesia, Caribbean, Great Barrier Reef, these really cool places. And he's been extensively involved in the IODP and the Pages 2K projects. Right, and then Hussein Sayani received his PhD in Earth and Atmospheric Science from Georgia Institute of Technology, and he worked there as a research scientist for the past 3 years. His research focuses on reconstructing regional changes in ocean temperatures and hydrology using coral proxies to better understand how and why Earth's climate has changed in the past. And he's currently a senior scientist at SLR, specializing in carbon management and climate change consulting. So I'll pass it to Thomas. And if you have any questions, you could just add them to the chat. And just a reminder again, keep your mics and cameras off if you can. Thanks so much.
Yeah, good afternoon from Bremen. Hello, everyone. Thanks to Pages for inviting us today. Thanks to Nikita Kauchal for moderating this event today. So the first talk will give an overview on reconstructions of hydrology and temperature from tropical corals. I will provide some examples from the last interglacial to the Anthropocene, mostly based on work we did at Marum with a number of colleagues during the past years. So this is our archive, massive coral colonies growing in the shallow waters of the tropical to subtropical oceans. These corals incorporate geochemical and isotopic traces into their carbonate skeleton. And these proxies then reflect the environmental conditions in the ambient seawater during growth. So these corals, like the one on the left from the Northern Red Sea, can grow for centuries at rates of 1 centimeter or more per year. However, to get paleoclimatic information beyond the last centuries, the community relies on fossil corals, recovers fossil corals like the one on the right. These can be radiometrically dated, and if they are well preserved, provide similar information on similar quality compared to modern corals. X-ray images of these corals can reveal the annual density banding pattern, which is quite distinct in the subtropics and becomes less clear if you're approaching the equator. However, the annual density banding pattern gives you a first estimate of the time interval that is contained in a coral record, like this modern coral on the left, which started growing in 1872, or the fossil coral on the right, which grew for time interval of about 100 years during the Holocene. So what are these paired coral strontium-calcium and data-18 records? This seminar today is dedicated. So actually this means we are analyzing 2 different proxies on splits of the same carbonate powder sample of coral carbonate. Coral strontium-calcium is a proxy that tracks temperature changes. Coral data-18 is a proxy that tracks the combined changes in temperature and seawater data-18. And seawater delta-18 is, like salinity, related to hydrological changes. So here we have 2 examples where both coral data-18 and strontium-calcium show essentially the same, documenting the annual cycle of sea surface temperature on the left during the last interglacial and on the right during the late Holocene, showing a higher temperature seasonality during the last interglacial. So this is an example from the arid northern Red Sea, where the coral data-18 signal on seasonal timescales is mainly driven by temperature. But if we are going to tropical Eastern Australia, these are very early results by Mike Gagan and colleagues. We see on the left that the coral data 18 signal deviates from the coral strontium-calcium temperature signal. And this is a clear indication for a seawater data 18 signal, which can be interpreted as a freshening. So using these two proxies, coral strontium-calcium temperature and coral data 18, it's possible to remove the temperature component from the coral data 18 to get ideas and estimates of data 18 seawater, hydrological changes at the sea surface. So from the Great Barrier Reef to the tropical Atlantic, where on the island of Bonaire, we have Holocene coral boulders lying on top of a reef terrace, which grew during the last interglacial warm period, some 125,000 years ago. And also from these fossil corals, it's possible to generate monthly resolved records, paired records of coral strontium-calcium and delta 18 for the last interglacial, 40 years for the last interglacial shown on the left, 70 years for the late Holocene shown on the right. And both proxies primarily track the temperature seasonality in the tropical Atlantic at that time. These wonderful records are part of a larger compilation, which is mainly based on the work by Cyril Géry and Will Brokas. And this larger compilation is shown here. At the top, we see several time intervals of coral strontium-calcium temperature records. In the middle, we see the corresponding coral data 18 records. And at the bottom, we see the calculated, reconstructed seawater data 18 variability derived from the combination of these two proxies. So we see time intervals from the last interglacial to the mid to late Holocene into the modern time. What is quite interesting here that for some time in windows, you see a, let's say, an opposite pattern of coral strontium-calcium temperatures and coral data 18. So for this mid-Holocene coral, we see a cooling trend over an interval of 70 years, which is accompanied by a freshening trend as evidenced in the coral data 18 signal. And we see also at a decadal timescale, a similar oscillation during the late Holocene, a cooling associated by freshening. What I'm trying to say is that if you would only have coral delta 18, you would indicate here during the mid-Holocene a freshening trend. No, if you would only have coral delta 18, you would interpret this trend as a freshening or a warming. But because we have coral strontium-calcium, which indicates a cooling, the coral delta 18 signal actually reflects a freshening. And we see also this opposite pattern between coral strontium-calcium temperature and coral delta 18 in a totally different set of corals, different species, work by Henry Wu. These are time intervals from the Common Era clustering around 1,000 years ago. Similarly, we see a cooling trend over a period of 50 years, which is associated by a freshening trend. And we also see high amplitude oscillation, which are higher than what we know from the period of instrumental observations. So saying it again, if we would only have coral data 18, this would be interpreted as a drop into cooler or drier conditions, but the coral strontium-calcium indicates warming. So consequently, the combined result is we have an event of warming associated by more saltier, more saline conditions. So I've talked about a little bit about the last interglacial, the Holocene, the Common Era. So I somehow missed the last glacial, and there are two reasons for that, because this is a 2K seminar. And the other reason is it's so difficult to get corals from the last glacial, because the reason is sea level was about 100 meters lower than today during the last glacial. So in order to obtain these glacial corals, you have to involve ocean drilling as done by IODP, the International Ocean Discovery Program. And this has been done at Tahiti some years ago. And for instance, here are results of a coral which grew 15,000 years ago during the early last glacial termination. And on the left, you see again paired coral strontium-calcium SST records and coral data-18 records, which document the annual cycle of temperature during a period of about 20 years. However, if we remove the annual cycle from these records and just look at the interannual variability shown here, the coral strontium-calcium SST shows pronounced variability at typical El Nino southern oscillation periods. If you just would have coral data-18, you wouldn't come to that conclusions. That's quite interesting. So, approaching now the last centuries, the advantage of these paired coral strontium-calcium and data-18 records from the modern corals is that they cover the period of instrumental observations, but they also extend beyond into the early 19th century or even into the late Little Ice Age. In this example from the Northern Red Sea, again, coral data-18 on seasonal timescales primarily reflect the annual SST cycle. However, if you do annual averages for both of these records, which are shown here, you see that the annual average coral data-18 record shows a totally different evolution compared to the coral strontium-calcium temperature record. So, for instance, this anomaly during the early 19th century from coral data-18 alone would be interpreted as a cooler or drier interval. However, coral strontium-calcium indicates there was no cooling at that time. So combining these proxies tells us that prior to 1850, we had even more arid conditions. And this is actually what the coral data-18 signal reflects. Another example showing that even during the so-called instrumental period, these paired coral strontium-calcium and data-18 records can have some or provide some surprises. Again, here coral data-18 on seasonal timescales is mainly reflecting the SST annual cycle, as we can see by strontium-calcium temperatures or uranium-calcium, which some people also consider as a temperature proxy in corals. If you look at the annual average records, we see that during the last century, coral strontium-calcium SST and uranium-calcium SST are quite similar, nicely tracking instrumental SST from this small island, Ogasawara, in the subtropical northwestern Pacific. But the coral data-18 record really shows a totally different evolution. Combining these three proxies to calculate seawater data-18 shown below indicates that the seawater data-18 reconstructions reflecting hydrology, the sea surface, nicely tracks interannual to decadal variations in sea surface salinity as derived from a reanalysis product. The most striking feature in this coral record is an apparent freshening of this region occurred at the turn of the last century, so in the early last century, around 1910. So, a final example is from the tropical Pacific Ocean from Kim Cobb's group, work published by Inta Nurhati. Here in the coral data-18 record at the top, we see a freshening or warming during the most recent decades. But the coral strontium-calcium temperature proxy indicates there was no warming, which is consistent with the instrumental SST. So combining coral data-18 and strontium-calcium to calculate seawater data-18 now shows us that most of the trend in the coral data-18 is actually reflecting a trend towards wetter conditions. So these paired coral strontium-calcium and data-18 records are a nice tool to provide seawater data-18 reconstructions, like shown in this compilation done by the PAGES Hydro2K consortium some years ago. This is based on the work of numerous individual authors. We see trends in different corals from different ocean basins. And in order to investigate all these things in more detail, we launched initiated a couple of years ago the PAGES Coral Hydro2K project. This project, well, builds on earlier efforts and work by Page's Ocean2K, a project which used a large number of coral records to reconstruct tropical sea surface temperatures for the past 4 centuries. However, at that time, the compilation contained only 10 paired strontium-calcium and delta-18 records. For instance, in the Indian Ocean, there's only one strontium-calcium record available, or was available at that time. So, just as a take-home message, this is paired coral strontium-calcium and delta-18 records suggest that the sea surface temperature and hydrology as reconstructed from these records not always changes in parallel. So this relationship between sea surface temperature and hydrology is definitely timescale dependent if we are thinking about seasonal versus decadal, interannual, or multidecadal and trans. At timescales like this, the relationship between sea surface temperature and hydrology depends definitely on the location where you are. If we are thinking about subtropical versus tropical or equatorial sites, and it's also definitely dependent on the climatic boundary conditions and other local factors like the influence of large-scale ocean circulation changes. So that's it for the moment. Thanks for your attention. And please stay tuned for the next talk by Hussein Sayani.
Thank you for that. So, so Thomas, I think, provided an overview of why, or the advantages rather, of using this paired delta-18 and strontium-calcium approach, to reconstruct hydrology, which is something that hasn't really been done on a large, either regional or even global scale yet. And so that is something that we wanted to do as a group. And so today I'm going to tell you, talk to you a little bit about this new database that we have finally completed and will be publishing very soon. But before I do that, I want to highlight that this database was developed by an amazing group of people, all of whom are showed here, and I'm incredibly privileged to have worked with them for the past year or so and to be here speaking today on their behalf. I want to flag in particular Rachel, who has somehow translated the group's sort of collective will, if you will, into a database, and also, Jessica Hargraves, Bethany Ellis, Hetty, I'm sorry, I'm not going to try and pronounce your last name, but she's on this call, and Logan and Ariella, who spent a lot of time QCing all the data that went into the database and the metadata, and there's a ton of it. And then of course, Nick McKay, who helped us take our database and put it into lipid format, which I'll talk about in just a second. So, so as Thomas mentioned, Coral Hydro2K was born out of this idea to simultaneously investigate the changes in tropical ocean temperature and hydrology over recent centuries. And previous attempts have primarily focused on temperature, but as you saw from the slides before, we can have completely different trends in both temperature and hydrology, particularly over long timescales. So on seasonal timescales and interannual timescales, these changes are tightly coupled across many parts of the ocean, but on longer timescales, these trends can be decoupled. And so we really want to look at them individually. But in order to sort of realize this goal, there are several steps in the way. The first is we need a collection of coral records, and we need these records to be stored in a standardized way using a standardized set of metadata. And then the next phase of this is trying to understand how to take those records and convert them into our climate parameters of interest. And so this would be things like temperature or salinity. And there are ways of doing that, but as I'll sort of talk about a little bit later, there are a lot of uncertainties, and having this data set provides us with an opportunity to finally investigate and try and come up with a set of best practices. And then finally, we have this phase 3, which is where we want to end up. This is the reconstruction of tropical ocean temperature and hydrology over recent centuries. And we're hoping to use both a coral proxy only approach, where we reconstruct these fields based on just the proxies themselves. And of course, we also want to incorporate data assimilation into our reconstruction as well. So we're hopefully going to have two parallel approaches when we get to that stage. So today I'm mostly going to focus on phase one, which is the database creation. So one of our first goals was to create a database that has paired strontium, calcium, and delta-18 records and stores them using a targeted set of metadata that identifies each coral record and informs the use of its proxy data. And so a little bit about our data structure. So we started with published coral, delta-18, and strontium calcium records that were at least 10 years in length. We sourced these records initially from Ocean 2K and then ISO 2K, as a lot of the Coral Hydro 2K team members were also worked on these groups, and we didn't really want to duplicate those efforts. And so we started with those records, and then we added a lot more. And what we added were primarily records that did not meet the selection criteria of Ocean 2K or ISO 2K, primarily because they were too short, or in the case of Ocean 2K, they were just strontium calcium only records. And then we also added a lot of records that were published more recently. So Ocean 2K was, I believe, last updated in 2015 or so, and then ISO 2K was the most recent records in there are, sorry, ISO 2K is about 2015, Ocean 2K is a little bit later. And so we have a lot more recent records in Coral Hydro 2K as well. The metadata that went into, so along with these coral records, we also have an extensive set of metadata, not as extensive as ISO 2K, but we did try our best to follow these crowdsourced and community-based recommendations that are published in MARPA, and the reference for that is here, and then in PAX 1.0. So this includes geographic and physical sample metadata, so location coordinates, depths, core names, coral species, etc. We include publication information, so and this includes DOIs for the original publications and any publication associated with a particular record. And then we also have links to the public archives from which we downloaded the data. So to links to either NoAA or Pangea. And then we have a lot of information about, or metadata about, the calibration of those records to SST, if those values were provided in the original publication, analysis metadata, so sampling methodology, the analytical technique used, and then of course we have uncertainty information as provided in the original publication. So all of this was collated by the group over I believe a year or so, and we're feeding all of this into Lipid, which is the linked paleo data framework that was developed by Nick McKay and Julian Emile J and published in 2016. And what is ideal about this framework is that it is a standardized way of storing this information. It is also a format used by previous Pages 2K products. And so in that sense, this database will be consistent in format and structure with previous databases. And so it's easier to use. And then the other nice thing about using Lipid is that we are able to get serializations of the database for MATLAB, Python, and R. So no matter what your coding language is, you will be able to access the data, which is really convenient. A couple things that are maybe a little more unique about Coral Hydro 2K is that since we are a much smaller database compared to some of the previous Pages compilations, and we're very much focused on a single proxy, we're able to do annual updates. So part of our team will be dedicated moving forward to adding new records to the database and publishing a new version of the database every year. And we're hoping to crowdsource these new records. And so we've developed a data submission form that will be posted with the database. And so if you are a coral paleoclimate researcher and you publish a data set, we would encourage you to use that form to submit your data if you would like it to be included in this database. And otherwise, if it's not, and if it's published elsewhere, we will hopefully find it, but the crowdsourcing will hopefully make this process easier and more manageable. So here is our coral hydroclimate network. This is version 1.0.0. Rachel is probably on this call saying it's not, but I'm going to call it that because we're there. So the records in the database are sorted by tier. These tiers are based on the availability of paired delta-18 and strontium-calcium data, record length, and resolution. They're not a value judgment. Every single coral record matters. This is just handy for our own internal purposes, and so we decided to keep it. As Thomas mentioned earlier, Ocean 2K only had 10 paired strontium-calcium delta-18 records and only had a total of 57 records total. The Coral Hydro 2K thus far has about 227 individual coral proxy records sorted into these 3 tiers. And so tier 1, which covers most of the 20th century and offers the highest resolution of paired strontium-calcium and delta-18, is shown in red. Tier 2 is kind of the same as tier 1. The records just cover less than 80% of the 20th century and potentially extend beyond the 20th century. And then tier 3 are also paired records, but these will have annual or lower resolution. So so the points over here show where these records come from for the most part. And then once we got those 3 tiers into the database, we decided that we wanted to just go ahead and add all the other delta-18 and strontium-calcium records that are out there that are not paired to the database, because these are still useful for a number of different applications. So in the case of delta-18 only records, these records will still contain a lot of information about hydrology and temperature, and they may be useful for paleo data assimilation approaches. They may be useful for calibration studies. And so tier 4 and 5 have delta-18 only records sorted by their resolution. So tier 4 is monthly to seasonal resolved records. Tier 5 is annual and lower resolved records. And then tier 6 and 7 are basically the same as tier 4 and 5, but now for strontium-calcium only. And so this is our current network in terms of spatial coverage, looking at temporal coverage. We note that most of the records fall between 1800 to 2020. So one of the advantages of working with corals is that they provide monthly resolved records or seasonally resolved records, which is unparalleled in the realm of marine proxies. The trade-off here, of course, is that corals only live for a few decades to centuries. And so most of the records in the database come from living coral colonies, or what we call modern corals. And so, so it kind of makes sense that the density of the database or records in the database is concentrated in the first couple hundred years. And then about 30% of the records in the database extend beyond the 1800s. And these records come primarily from fossil corals, and you can see them over here. These are these discrete windows of time that extend back to about 200 CE, and they're of course discontinuous. So one of the things that we can do when you have an entire database of corals is figure out when these records were published and versus when they were collected. And the reason we did that is you can't get a bunch of coral people in a room without somebody eventually waxing poetic about the heyday of coral drilling in the early 80s. And so we decided to see if that's actually a thing. Turns out it's not entirely a thing. There is, in fact, a delay between when the a 5 to 15-year delay between when corals are actually cored and when those records are published. And so think of this as me calling out everybody that is sitting on coral records from, that were collected 10 years ago, please publish them. But what we did find is when we look at where these records are collected over time, there's a bit of a trend. And so that's what's plotted in this map over here. So the dots or the markers that are more green are corals that were collected more recently. The markers that are shaded blue or pink are cores that were collected a lot later. And you can see that in general across all ocean basins, the more recent records are collected closer to our continental margins, and fewer records over time are being collected from these remote, far-flung regions of the tropics where we actually need that data, right? These are the most data-scarce regions of our planet. And so if this and other figures along this vein will be available in our manuscript that we're about to submit. So feel free to drop them into your next proposal to help provide some, justification for what you're doing. So one of the other things we wanted to do is look at how well records in the Coral Hydro 2K database capture local SST and hydrologic variability. So this plot is by no means groundbreaking unless your entire sponsored program development relies on saying strontium-calcium doesn't work. And so if you look at the top two panels, these are the ones with markers that are shaded blue. These are correlations between records at each of our strontium in the top panel and delta 18 in the middle panel records, and sea surface temperature from the grid box closest to that record. We used ERSST and only calculated correlations from 1950 onwards. And so the circles denote correlations that are significant at 95%, and squares are correlations that are not significant. So in general, we can see that most of our records are fairly well correlated to SST. I want to point out that these correlations are calculated at annual resolution. We have a similar set of plots that show correlations at bi-monthly resolution. And as you can imagine, because there are seasons in SST and there are seasons in coral records, all of those correlations are much higher, right? So not as interesting to look at. But here we can see that in general, both our strontium-calcium and our delta 18 records are tracking SST. Not mind-blowing, but reassuring. So this tells us that our database is actually going to be useful for reconstructing local SST and local SST variability. Trying to look at how well delta 18 captures hydrology is a little more complicated, because we would ideally want to compare our coral delta 18 records to delta 18 seawater records, but those don't exist for the most part. And so what we have in this bottom panel over here is the correlations between annual delta 18 at each site and annual sea surface salinity from the EN4 data set. I want to note that we can do the same thing with a different salinity product, and this map looks totally different. So there are pretty large inconsistencies in our sea surface salinity data sets, at least the ones that are currently available, which again just highlights why such reconstructions are really important. But in general, we can see that we have decent annual correlations between most of our records and sea surface salinity. To the extent that you can trust this, I would take it with a grain of salt. And then we took this idea from the most recent Pages 2K temperature publication. And what's plotted over here is the correlation between each grid box, SST in each grid box, and the highest correlation between SST for each grid box and coral records within a 300-kilometer radius. And the way, what I like to describe this plot as showing us is the reconstruction potential of the database. And so you can see that even though each of these records is, sitting, capturing what's happening at one particular location, if you were to do some kind of climate field reconstruction, you could safely use these records to reconstruct large-scale regional variability. And of course, correlations are again higher on bi-monthly timescales and a little bit lower on annual timescales. And this is again simply because we have the seasons being tracked over here, and they're just going to inflate our correlations. So the annual scale correlations are kind of what you want to focus on in terms of where this database would be most useful. So this brings us back to our project goals. We now have a database. We can move forward with our phase 2 and phase 3. So that's what I'm going to talk about next. So our phase 2 objectives are trying to understand how to go from these coral proxies, which are kind of difficult to understand or interpret in the real world context, and convert them into, sorry, this should say SST, either temperature or either hydrology. And so there are 2 parallel efforts underway here. Both of them have just started. I'll show you just a few results from one of them and a shout out for the second one. So one of the issues that I think is well known at this point is that strontium-calcium calibrations are inconsistent across publications. So here's a plot that summarizes the different strontium-calcium to SST calibration slopes published over the last couple of decades. And you can see that there's a huge spread. And this is kind of a problem because you apply the wrong calibration to a record, you get a completely different reconstruction, right? So some of the potential sources of this inconsistency would be intercolony variability. So corals growing in the same reef sometimes have slightly different records, and that, again, just gives us different calibrations. There are also sampling and analytical differences that are feeding into the spread of slopes as well. And then there's calibration methodological differences. So this would be the type of data treatment, the regression methodology, and the choice of SST products and errors. Now, we can't really account for intercolony variability or these analytical differences, but we can, now that we have all the records in a standardized format in one database, we can actually standardize our calibration methodology and look at what comes out when we apply the same regression type or use the same SST product on all our records. And so this is a effort led by Matt Fisher, and the results are interesting. So plotted over here is the calibration slope versus the R² value between strontium calcium and sea surface temperature. And we took the exact same records and we applied 3 different regression methodologies to them that are commonly used in most publications. This would be ordinary least squares, reduced major axis, and then weighted least squares, which is also BLS. And you can see that you get a huge spread of slopes where your R² between temperature and strontium calcium is on the low side. But what's interesting is when your R² value increases, all of these slopes start to converge. And where they're converging is also interesting. This is about 0.06 millimole per mole, which is a number that means absolutely nothing to anybody that is not a coral person, but that is the average strontium calcium to SST calibration slope amongst all the published records. And so it's interesting. What this tells us is that if your R² value is low, your choice of regression matters a lot. And we have a little bit more work to do in figuring out which regression method would be most appropriate. But if your R² value is high, then it really doesn't matter how you calculate your regression. You will arrive at a very similar answer, which is interesting. We have a lot more work to do. Of course, this plot looks totally different if you use a different SST data set, which is interesting. And some of these SST data sets provide errors, some don't. And so our next phase is going to dig into into these issues and come up with a set of best practices for calculating the strontium-calcium to SST calibration slopes, which are an important piece of trying to convert these paired strontium-calcium and delta-18 records into hydrology, right? So that is one of the two coefficients that we would need in order to do that conversion. The second piece of that equation is sort of understanding this relationship between delta-18, coral delta-18, the delta-18 of seawater, and then sea surface salinity. This is a bit of an open question at the moment. So plotted here is a figure from Stevenson et al. 2018, which compares coral-derived delta-18 seawater versus modeled delta-18 seawater. And I'm not going to go into this plot because I think I'm running out of time. But in general, they don't look the same. And so there's some questions about our derivation methodology for delta-18 seawater, the forward modeling approach, or our proxy system models. And so now that we have all these records, we want to sort of try and dive into that because that is something that really hasn't been done so far either. And it's, again, a critical piece of the equation needed to convert these paired delta-18 and strontium-calcium records into delta-18 seawater or a hydrology reconstruction. So to help us with this effort, we actually, to make progress with this effort, we actually need your help. So if you are a researcher that is, in the business of water isotopes, particularly seawater isotopes, and you have published delta-18 seawater data, you've probably realized that there's not a good place for you to archive them. Well, Coral Hydro2K is providing you with that place. We are in the process of creating a second database. This is going to be a database for delta-18 seawater records that have been published since Legrand and Schmidt, because that data set stopped adding records in 2009. So for the past 11 years or so, these records have had nowhere to go. So you can quickly scan this QR code or go to this link and submit a record if you have them. And these records will help us try and tease out the relationship between coral delta-18 seawater, and sea surface salinity, which can then be used to inform our reconstructions. And then finally, this is part of phase 3. This is kind of where we're going, and I think this is probably the topic of one of the upcoming Pages 2K seminars. So I'm not going to go into this too much. This is work being led by Sarah Sanchez and Feng Zhu. But basically, the database allows us to use coral records or incorporate coral records into the last millennium reanalysis framework and basically combine both this model and our observations to get a reanalysis product that is hopefully a little bit better than a coral-only reconstruction. So when I say we, I mean Sarah. Sarah did some initial tests and they look promising, but again, we kind of need to figure out those calibration pieces in order to do this properly. So this is on hold at the moment, but we'll hopefully get to it very soon. So in summary, our Coral Hydro2K database is now complete. It contains a total of 227 strontium, calcium, and delta-18 records, many of which are not included in other Pages 2K compilations. 70% of the records cover 1800 to present, and about 30% extend beyond the 1800s. So if you have fossil coral records that are not archived or you're hoping to publish them soon, please send them to us. We would love to include them and fill out our database. Our records, for the most part, track large-scale seasonal or large-scale SST and SSS patterns or hydrology patterns. And keep your eyes peeled. This database is coming very soon to Paleo Data Archive near you. It will be hosted on the Pages 2K website, on the Lipidverse, and on NOAA Paleo. So we're pretty excited to get this out there. And then our next steps are to sort of dive into our understanding of how these coral proxies map onto our climate parameters that we're interested in. And then eventually we're going to move towards reconstructing past tropical hydrology and SST trends over the last 200 to 300 years. So if you're interested in any of our next steps, please feel free to reach out to me to join our team. We're happy to bring on new people, new ideas. All of these projects are just getting started. And so if you are interested, this is sort of the time to hop on board. With that, I think I'm done, and we will now take questions.
Thanks so much, Thomas and Hussein, both. That was really brilliant. I enjoyed it very much. You could ask questions in the chat, or you could raise your hand, then we can call on you, or you could just ask a question, whichever format you would like. I can quickly jump in with a question while I have you here and there's time. Is precipitation minus evaporation, is that a problem, or can we reconstruct that using oxygen and strontium-calcium? Like this precip minus evaporation balance at the sea surface?
Yeah, it can be reconstructed. Precip minus evaporation, then reflecting the delta O18 of the seawater, so hydrologic balance at the sea surface.
Yeah, exactly.
But there are many things which you have to consider too, like the delta O18 of the precipitation, or the delta O18 of the seawater affected by ocean currents or upwelled from deeper waters. So it's a complicated issue, but it's possible if you consider all the factors affecting this.
Okay, thanks, Thomas. Mary, would you like to ask?
Hi, hello everybody. Thank you very much for those talks. I really enjoyed them. I had a question for Thomas, and I also had a question for Hussein. The first one, if that's possible, I don't know, let me know. But the first question I had was about the, you showed a map which showed the areas where you had, where you absolutely required to have SST and delta O18 measurements. And so I was wondering if we could use the models, climate models, to kind of map the areas where we know that we critically need to have strontium, calcium, and delta O18 combined, and areas which are not so important in order to be able to increase the kind of it's an issue getting the paired samples, because it just costs a lot of money and time to get these records, and we're all limited in that sense. So I was just kind of thinking as I was listening to your talk, if we could use kind of models to kind of climate models to kind of find the areas which are critical, where we critically need both proxies if we want to get at the variability. So I suppose that question could be to either of you. Don't know.
I have an answer, or maybe a little bit of an answer. So there's a paper published by Ruslan et al. In 2013 that has this fraction seawater metric, and I think that is kind of getting at what you're asking. So that looks at the relative contributions of hydrology and temperature to variability in coral delta 18 records at different parts. And what they do find is there are indeed some parts of the tropics where there's a strong fraction seawater component to our coral delta 18 records, and there are places where that fraction is a lot lower. And so, for example, the West Pacific, that fraction is going to be a lot higher because there's a lot more complicated. The precipitation and advection patterns are a lot more complicated over there, right? And then in the Central Tropical Pacific, Christmas Island, for example, it's primarily a P minus E balance, right? It's just that's the predominant driver of salinity. So So yeah, so that would be one resource. I know ISO2K has sort of updated this, and they're getting a new paper out very soon on the topic as well, and that looks at how you can use pseudocorals to inform where you might, be able to, where you might need these paired records. That being said, we for fun tried to calculate the fraction seawater using actual corals, and it didn't go quite so well. So there again still questions about our current understanding of how temperature and sea surface salinity actually relate to coral delta 18. So that is something we're hoping to answer more specifically. But for now, I would say the Roussan paper and this coral ISO2K paper, I believe, is being led by Diane Thompson. Those are probably going to be your best resources at using climate model or SST and salinity from climate models to figure out where you may want to apply a paired approach and where you might not. Hopefully that answers your question.
Yep, thank you, thank you. Do I have time for a second one? Can't hear. Okay.
I don't see any other takers, so it should be.
Okay. So
there's one in the chat now, so maybe quick question.
Okay, just very quickly. I really liked the plot that you showed. That was in Hussein's talk with the variations of the R square between the strontium-calcium and the SST as a function of the different methods that you used. And I was wondering if there again, there's some kind of micro-environmental effects, so that there's sites which are going to not be as representative by the kind of big squares that we use when we're using the satellite data. So we're just kind of wondering if you had also kind of taken out those sites, or if you treated them differently, if you'd had some kind of reflection about that.
So that is kind of the next phase of that. So that was a very initial analysis that we conducted almost over a year ago, and then we kind of shifted focus entirely on the database. The difficulty is, so ideally we would do that by getting the highest resolution SST data set out there, which is on a 0.25 by 0.25 degree grid. And that is going to give us a much smaller grid box. That data is not available, or that data just starts at 1980. A lot of our coral records don't extend that far into the present. So our overlap between our SST, this high resolution SST product, and our coral records is maybe 10 years in a lot of cases. And it's just not enough to do a proper comparison between a smaller grid box and our strontium calcium records. But there is a bit of work out there that does show what you're suggesting, which is the finer the scale of your SST product, the more consistent calibrations you do get. And I think Christine DeLong has published some of this work primarily with Pseudoastrea siderea corals, or is on her way to publishing it. That does show when you use these high resolution data sets, you can get more consistent calibrations. I don't know if you had anything to add, Thomas. I feel like I'm doing a lot of talking.
Just to add, referring to the figure you mentioned, Mary, we didn't do any pre-selection of the records in terms of microhabitat on the reef to derive this figure. It just popped up the pattern. Matt Fisher did the analysis, came out of what we had. So I would say we can include microhabitats on the reef as a result of this pattern. Yeah.
Well, thanks, Thomas and Hussein. Thanks, Mary. There's a question in the chat. It says, are you compiling other elemental proxies? So magnesium, lithium, uranium, carbon isotope?
We didn't talk about that in the large-scale Hydro-2K group yet. I think we could. There are not so many lithium, calcium, magnesium, calcium, uranium, calcium records out. Technically, we could. What do you think, Hussein?
I think it's come up a couple of times, and yeah, that was I think our focus at this point has been on del-13 and strontium because those are the most commonly used proxies, and future updates can certainly include these newer proxies, and we may want to anyway because people are publishing more and more records with them. But yeah, to Thomas's point, at the moment, there just aren't very many of those, and the ones that are there aren't very long. So adding them in future updates wouldn't be too difficult. So we just kind of put that off to the side in the interest of time. But yeah, so if you're interested, you should join the database update team, and you can spearhead the incorporation of additional proxies. This is entirely open, so to what the community's will is. So feel free to hop on board and add those records. We would love to have you.
Sounds good. Yeah, especially carbon isotopes, because they must be measured along with the oxygen anyway. Sounds good. Any burning last questions? We just have a minute to go. Otherwise, I should close it. I can't see any heads up and nothing in the chat. Okay. Thank you so much, Hussein and Thomas. That really was great. I learned a lot and really enjoyed the presentation. Thanks for taking the time. The recorded version will be available on YouTube in a couple of days, so you could always watch it there as well. And just to announce, the final seminar of the 2K Network Seminar Series will be given by Sylvia and Greg on the 8th of November at 1700 UTC. And it's on proxy system modeling and the last millennium reanalysis, so something that Hussein already touched on. I'll just put the link in the chat, and then we're done for the day. And thanks everybody for joining.